All right. Hi, guys. Welcome back. Today we're talking about the Pauli exclusion principle, which is section 5.16 on your CK12 packet. Okay. Today's date is November the 19th. We're doing 5.16, just a reminder. And it is exactly what you see here in your packet. It's just in a PowerPoint presentation, just like we've been doing lately. All right. So, the introduction. Can you name one thing that easily distinguishes you from the rest of the world? Yeah, Alexia.
And we're not talking about DNA. That's a little expensive to sequence. For many people, it is their email address. My email address allows people all over the world to contact me. It does not belong to anyone else, but serves to identify me. Electrons also have a unique set of identifiers in the quantum numbers that describe their location and spin.
Thank you. So, if you've ever tried to create an email address using like your name, like, Oscar, if he's going into Yahoo or to Gmail to create an email that, that's brand new, well, maybe he might use part of his name, like O. Mendoza, right? Because that's his last name. Well, he might not be able to use O Mendoza because, there's a lot of O Mendozas out there. He probably can't even use Oscar Mendoza because Oscar's a pretty common name. Mendoza, there's a lot of people with that last name. But he can add something that will make his email address unique and probably different than everybody else in the world. He can probably add a couple of numbers, right? And that will change that email address so that it's unique and that anytime you type it in so that you can send him something, it's going to go directly to him. So electrons also have an address. We call it something different. We call them quantum numbers. And basically it's a there are four different numbers that make up the quantum numbers, okay? And these quantum numbers tell us the energy levels, it tells us the orbital, and if there's more than one orbital, like a P, D, and F, it'll tell you which one of those. And then the last number is like one of those numbers that Oscar puts in after his name. It's known as the spin number. Okay. So here is we're today's topic, Pauli exclusion principle, and I included a picture to show you the four quantum numbers that make up an electron's email address. Okay, hypothetically speaking, right? So the first one is known as the principal quantum number. The symbol is N, and that's the energy level that you'll find it, right? The period. The period. We know there's 7 periods on the periodic table. The second quantum number is the angular momentum. And the angular momentum is shown by the symbol L. And it's these orbitals that you have down here. The S orbital, the P orbital, the D orbital, and the F orbital. We have 4 types, right? The magnetic quantum number, if you have more than one, and I actually have a picture down here that shows you that M sub L. For the S orbitals, there's only one. So you have that 0 for M sub L. But everything else, all the other orbitals have multiples of them. So these will tell you which one that electron can be found in. The spin quantum number can either be a positive 1/2 or a negative 1/2, right? Each orbital can hold 2 electrons. So one of those electrons will have a positive spin, the other electron will have a negative spin. Okay? 3 out of the 4 quantum numbers can be the same, the first 3. But it's the last spin number that has to be either positive or negative. Okay? And that is what makes up the total address for these electrons. Okay? When we look at the orbital possibilities for a given atom, we see that there are different arrangements for electrons for each different type of atom. Since each electron must maintain its unique identity, we intuitively sense that the four quantum numbers for any given electron must not match up exactly with the four quantum numbers for any other electron in that atom. Okay? So let's say, and we have an example that we're going to be talking about. We're talking in the next slide about helium. Okay? We're talking about helium because helium is element number 2. So it's going to have 2 electrons. And we're going to show you how different that address or these quantum numbers for these electrons are. Okay? And part of those quantum numbers might be the same, but there will be part of that quantum number, that set of quantum numbers, that will make it unique. All right, true or false, guys? What do you think? The four quantum numbers for any given electron must not match up exactly with the four quantum numbers for any other electron in that atom. Is that true? Did we just read that in the last slide? If we did, it's true. If I changed it, then you should put false. What do you think? Did I change any of the statement, or did I not change the statement? If I did not, put true. If I did change it in some way, put false. What do you think, guys? True or false? I only got 5 people in Pear Deck, so I better get some answers here in the chat. Very good, Mario. Mario has already posted, and I don't even have to ask. He's saying false. I have changed something in this sentence. What about the rest of you guys? What about the rest of you guys who are not in Pear Deck? Arlette, Hanya, Irvin, Kevin, if you are not in Pear Deck, I want to see an answer here in the chat. Very good, America. You're saying true. What about Hanya? What about Irvin? Or Irvin, you said you were in the Pear Deck, right? Oh, no, I didn't see you put that you're in the Pear Deck. Okay. So, Oscar, you've already answered in Pear Deck, I'm assuming. Alexia, I'm assuming you're the other person who's answered in Pear Deck. What about the rest of you? Gabby, Yoselin, Melissa, Caitlin. What about you guys? Have you voted? You're in the Pear Deck, Irvin. Excellent. Okay, let's see what they've answered. 4 students have said true. Fifth with America. And then another person has said false. So we got 2 people who said false. Okay, excellent. All right. If you picked true or if you picked false, the answer is true. That is a true statement. I did not change anything. It says here, and I didn't write the whole sentence because it goes on, but it says the 4 quantum numbers for any given electron has to be different. It cannot match up with the 4 quantum numbers of another electron. Okay? The quantum numbers, you can have 3 out of 4 the same, but you're never going to have 4 out of 4. True statement. All right, this is the example that I was telling you about helium. For the hydrogen atom, there is no problem since there's only 1 electron in hydrogen. We don't care. No, we want to talk about electrons or atoms that have more than 1 electron. However, if we take into consideration helium, we see that the first 3 quantum numbers for the 2 electrons in the atom are the same. Okay. So what's the same? Well, they have the same energy. They are in the same orbital and the same shape. Okay, so this is the energy level. That's the same. We know they're in the s orbital. That's fine. And since there's only 1 s orbital, they're both in there. Now, that's 3 out of 4. That's fine. You can have 3 out of 4 the same. But check this out. The spin is different. What differentiates the 2 helium electrons is their spin. One of the electrons has a positive 1/2 spin. So that's like saying this electron is going forward, while the other electron has a negative half spin. This electron's going backwards. That's all it says. Okay? And that's what makes the quantum numbers different. The first electron has the positive version. The second electron has the negative version. Therefore, the address, which is here, 100 positive 1/2, 100 positive, negative 1/2, that's your set of quantum numbers for the first electron and for the second. And you can see here in black and white in this example, 3 of them can always be the same. It's the fourth one that will always be different. You'll always have one electron with a positive spin, another electron with a negative spin. So the 2 electrons in the 1s orbital are each unique and distinct from one another because it's the spins that make them different. Which of the 4 quantum numbers makes electrons in helium different? And this is a multiple choice question. Let me put the choices in the chat for those of you who are not in there. So A, is it the principal energy level? Is it B, the orbital shape? Or is it C, electron spin? Hold on, America. Let me put all the answers for you. Which one is it? A, B, or C? Is it the energy level, the orbital shape, or the electron spin that's different? What do you think, guys? I got 2 out of 6 people in Pear Deck who've answered. That's fine. What about the rest of you? Efrain, Yaselin, Caitlin, Hania. I haven't heard anything from you guys today. Not even, well, as far as the lecture goes. A, B, or C? What do you think? 3 people here have said the energy level is what's different about those 2 electrons in helium that we just talked about. 4 people have said that it's the principal energy. 1 person says it's the orbital shape. What do you think, guys?
I think it's A.
You think it's A? Anybody else think it's something different? So we're talking about those electrons for helium that we just talked about. We're talking about the 2 electrons for helium. Oh, now all of a sudden everybody's changing their answer. 2 people have now changed it to electron spin. 3 people have changed it to electron spin. 4 people have changed it to electron spin. Why? Why are you changing your answer? Now all of a sudden you guys remember? Pues sí, miss. What is it that's different? The spins are different. They have the same energy level. They have the same shape of orbital. It is the spin that makes them different. It doesn't matter, Irvin. You had the wrong answer and then you remembered. Se prendió el foco un poquito tarde, pero se prendió.
Which one was it?
It was the spin. It was C. C, electron spin. Remember, one of them's be going forward, the other one's going to be going is going to go in a different direction, backwards. Forward, backwards. Forward, backwards. I can't do them at the same time. I can't do it. I don't know if you're one of those who's special and can do that. I can't do it. So now we get to the last part of our lecture, the Pauli exclusion principle. So all of that we talked about, everything that we talked about in the last 2 slides created the Pauli exclusion principle. And it says no 2 electrons in an atom can have the same set of 4 quantum numbers. You will never ever see the same set of quantum numbers for any 2 elements. That will never happen. You can have the first three the same, but the last one, the spin is either positive or negative. You cannot have two electrons with the same spin. So let's finish it off. Let's remind ourselves about the which ones can be the same. The energy of the electron is specified by the principal, angular momentum, and magnetic quantum numbers. Okay? Those three can always be identical. If those three are identical for two electrons, the fourth quantum number must be different. Okay? The spin number must be different in order for the two electrons to be differentiated from one another. The two values of the spin quantum number allow each orbital to hold two electrons. The figure to the left shows how the electrons are indicated in orbital diagram. Okay, so, and this picture should help you remember that it's the spin that's always different. Okay, one arrow will point upwards, the other arrow will point downwards. Those arrows represent electrons. Okay, in an orbital diagram, a square represents the orbital. So the box is the orbital, while the arrows represent the electrons. An arrow pointing up represents a positive or one spin direction, while an arrow pointing down represents the other spin direction. Okay? So it's because of the spin that we can fit two electrons. If we have two electrons with the same spin, they will not be able to fit in that orbital. It'll take too much space. All right, last question before we see the video. And I want to do it quickly so that we can watch the video. It's only about 1.5 minutes long, and maybe we can get you guys out of here early. Which of the following is not part of the four quantum numbers? And read them carefully, guys. Read them carefully. Let me put all four of them in the chat. A, is it the principal? QN is just quantum number, okay? Don't get that confused. Quantum number. B, is it the angular momentum? QN. C, is it the magnitude quantum number? D, is it the spin quantum number? A, B, or C, or D, guys? A, B, C, or D? A, B, C, or D? What do you think? Which one is not part of the four that we just talked about? Is it the principal? A, the angular momentum. B, magnitude. C, or spin. D. What do you remember about the last slide? America says it's B. Okay. Anybody else have something different? America says B. What about the rest of you guys? Yeah, Alexia says C. Anybody else? Let's see what they voted. Oh, look at that. Everybody's voting. 2 people say C, 1 person says B, 1 person says D. Oh, now everybody's voting for C. Why? Why? All of a sudden, everybody's changing it. Let's go back. So the first one is the principal. So that was there. That was A. Angular momentum. That was there. That was B. The spin is D. But I had magnitude instead of magnet. And somebody, Alexia, saw right through it. The correct answer is C. Very good. It is magnitude. Magnitude was not talked about. We said magnetic. Very good, Alexia. Very good. The rest of you guys who got that correct. All right, this is a video. It's about 2 minutes long. but I only want to watch the first part of it.
We have two particles with the spin half of unity, which can imagine as a top toy in the form of a half sphere. Suppose these two particles are identically, that is, they have the same internal properties or quantum numbers. We want to put them in the same place, for example, inside the sphere. There is some fundamental principle of nature, which usually called the Pauli exclusion principle, stating that no two particles with the spin half of unity can share the.
So right now they're talking about if these electrons have the same spin, can we fit them in this orbital?
The same quantum state at the same time. In our demonstrative example, this means that we cannot put in the same place, inside the sphere, two identical half sphere. However, we can do this if we flip vertically one of half sphere. In this case, our state will not have the same internal properties or quantum numbers. They will differ in the direction of the spin, or, more accurate, the projection of the spin. One half sphere will correspond to the spin up, while other will correspond to the spin down.
So here, the reason why you have a positive half spin, a negative half spin, is so that they can fit within the orbital. If you have two electrons with the same spin, they're going to want to take up the same area, and it's not going to fit in your orbital.
If we take a different particle, it will not feel these particles, and it can share place with any of these particles. This procedure is nothing as the construction of the proton and other subatomic particles from an elementary particles.
And then he starts talking about more college level chemistry. We don't need to study that stuff. All right, let's finish up our presentation. In summary, the Pauli exclusion principle specifies limits on how identical quantum numbers can be for two electrons in the same atom. Your review questions that you're going to be answering: what is the difference between the two helium electrons? 2. What does the Pauli exclusion principle state? 3. What does the two values for the spin quantum number allow?